Good evening, everyone. Uh, Today we had some challenge on from the speaker side. That's why the admin is actually presenting the today's session. So, uh, Ashwin, are you ready? Okay. Meanwhile, we'll wait for Ashwin to join the session. Let's talk about the topic what Ashwin is going to present today. So he's going to present a topic on gamma ray burst and the high energy universe. So basically, if you see the gamma ray burst, they are basically it talks about the high energy astronomy and astrophysics involving the study of astronomical objects that emits the radiation at a very short wavelength, that is X-rays and gamma rays. It also involves the study of a very uh, energetic particles such as cosmic rays and neutrinos. The universe is very rich in source of high energy radiation, and some of these sources are known to be far. And right now, we can see in the news more or less. We talk about powerful source of radiation in the universe that involves black holes, neutron stars, supernovas, extremely powerful. Nearly light speed of jets have been continually challenging our understanding of the behavior of the matter at very extreme densities and temperature, and in presence of enormous magnetic field and extreme gravity. Since many aspects of the physical mechanism that drive these sources are poorly understood, this is also one of the most active areas of research in astronomy and astrophysics. So I think we have Ashwin. Welcome, Ashwin. Welcome. We were just talking about your abstract, about your topic, and welcome to today's session on gamma ray burst and high energy particles. So let me introduce Ashwin about his journey. So Ashwin is basically former research in high energy astrophysics as well as amateur astronomer, educator, and he is great enthusiastic in spreading the knowledge of astronomy and science to students. He is native of Bangalore, Karnataka. After completing his schooling in Pilagres High School, he joined Canara PU College and completed his PU studies in science in 1997. Then he went to MIT Manipal and obtained a Bachelor of Science degree in Electronic Communication. He moved to US in 2003 and spending a year in graduate program in electrical engineering, he switched to his first love, that's physics. He then spent several years learning physics, gaining research experience in areas of physics such as nanotechnology, nonlinear dynamics, nuclear and particle physics, before committing to the research in high energy astrophysics. He has nearly conducted research in this field for more than 7 years, working along with scientists from NASA and Naval Research Laboratory. He has published dozens of papers in peer-reviewed journals like Astrophysics Journal and the monthly notices of the Royal Astronomical Society. Has almost 200 plus citations. He has also given several talks in various institutes, both at scientific level as well as general public. Apart from research, he spent much time in teaching physics and astronomy at US universities and also mentored several undergraduate students in their various research projects in astronomy. After returning to India, he has been actively involved in conducting astronomy and space education programs in schools and colleges, as well as programs for general public in and around Bangalore. So, with that, I welcome Ashwin for today's session, and we wish him the best of luck. Over to you, Ashwin.
Thank you, Mangesh sir. Thank you for having me here. It's my pleasure. So, can I begin?
Yes, Ashwin, please begin. It's all yours
Mangesh,
now.
will you be handling the slideshow?
Yeah, yeah. You just say next. We will change. Admin will change it.
Okay, okay, I'll do that. Okay, so what do we mean by high energy? High energy is energy with wavelength higher than zero point zero 0.01 nanometers. Okay, a nanometer is a billionth of a meter. So when we say high energy, we mean X-rays, gamma rays, and so on. So just to get a perspective of what that is, right? You have this little figure. It shows the increase in frequency, that is decrease in wavelength as you go from left to right. When we talk about radio waves, they have wavelengths of typically meters or tens of meters, right? For reference, they've shown size of buildings. Then as we go further down, we come to visible light, right? Visible light is of the size of, say, a virus. And coming to X-rays, X-rays are of the size of atoms, and gamma rays are of the size of nuclei or smaller. Okay, that is for comparison of the wavelength. Coming to the energies, which is at the bottom of this figure, just take a look at the typical visible photon energy. Now, because photons have very small energy, we use units that we call electron volts. Now, I won't go into detail or the definition, but suffice it to say that a typical X-ray photon has thousands of times the energy of a typical optical photon, right? That's the energy perspective. And gamma ray photons can be much, much more energetic. So a typical gamma ray photon has about 100,000 times the energy of visible light. But then there is no limit to the energy in which we observe gamma rays. So keV is kilo electron volts, 1000 electron volts. But we do see gamma rays all the way up to penta electron volts, right? That is a quadrillion times more powerful than visible light photons. In fact, in 2024, the Chinese LHAASO reported the detection of a 2.5 TeV photon, penta electron volt photon, from the Cygnus X region. Next slide, please. Okay, so this is a video. I hope it plays. Now, when I say boat, I don't mean the one that sails on water. Okay, so you observe a flash of light, right? Now, gamma ray bursts, or GRBs, as I will call them from here on, are by far the most powerful explosions in the universe. On the 9th of October 2022, a GRB exploded that saturated the detectors on board the Fermi Gamma Ray Space Telescope. This telescope is capable of detecting the most energetic. Can you go back to the previous slide, please? Yeah, I'm not ready for this slide. Yeah. This telescope is capable of detecting the most energetic gamma ray phenomena. So what you're seeing in this slide is a video of the flash of this gamma ray burst. But of course, it's gamma rays. We can't see it. So it's been artificially translated to optical. Now, follow-up of this GRB showed that it occurred 1.9 billion light years away. It emitted gamma rays for about 10 minutes and at its brightest had a power of about 10 to the power of 47 watts. Okay, that's 10 followed by 47 zeros. Now, just to put that into perspective, at its brightest, it's shown as brightly as a billion times a trillion of our suns put together. That's right, a billion times a trillion of our suns. This burst was so energetic that lightning detectors in India and in Germany were even able to measure the effect of this burst on the Earth's atmosphere, and this is from 1.9 billion light years away. Okay, this GRB was dubbed the BOAT, which stands for the brightest of all time. Okay, next video, please. Next slide. This is also a video. I hope it plays. Okay. So, what are these GRBs? GRBs are very powerful jets of gamma rays, and when one of these jets happen to point towards us, we detect it with one or the other of our gamma ray space telescope. Next slide, please. So this is the most active gamma ray space telescope right now. It's called the Fermi. Next slide. So this is also a video. What this video shows is the first 500 GRBs that were detected by the Swift satellite. Now, as you can see, GRBs occur in all parts of the sky, therefore all parts of the universe, and they occur somewhat randomly, right? We now know that they occur at a rate of about 3 per day from all parts of the universe. Next slide, please. Based on their durations, that is how long they last, we see two subclasses of GRBs. Long GRBs that last longer than 2 seconds and can last for even up to several hours, and short GRBs that last for fractions of a second, milliseconds, and up to 2 seconds. So what you're looking at there is the distribution of a large number of GRBs that have been observed. You can clearly see that there are two peaks in this distribution, one below 2 seconds and one above 2 seconds. Okay, next slide, please. So, based on decades of observations, analysis, and modeling, we have a reasonable picture of what GRBs are. Long GRBs are believed to occur during the collapse of a massive star. Right? This is the picture at the bottom. It's what we call a collapsar. While short GRBs are believed to occur during a binary merger event. That is when two compact objects, such as two neutron stars or a black hole and a neutron star, merge together. That's at the left top. In the case of a long GRB, scientists also expect a very powerful supernova explosion called a hypernova. And in the case of short GRB, they expect a unique kind of supernova that is termed a kilonova. Both of these extreme events are expected to produce large amounts of gravitational waves. Okay. Now, in the case of a long GRB, scientists, sorry, in both cases, a black hole is formed at the center, and twin jets, that is, one from the north magnetic pole and the other from the south magnetic pole, are emitted. Now, exactly how the gamma ray radiation is produced is still a mystery. Competing theories include the internal shock model and the magnetic recombination model, and there are many variations on these ideas. In the internal shock model, a fast moving shell of matter that is ejected later in time, shown in the figure, catches up with a slower moving shell slightly ahead that was ejected earlier and collides with it. So a fast shell that comes later catches up and collides with a slow moving shell. Because we're talking about shells that are moving at near light speed, the collision produces huge amounts of gamma radiation. In the magnetic recombination model, the ejected material is highly magnetized, and due to extreme turbulence, the magnetic fields combine. Sorry, Mangesh, did you send me an image? Okay, never mind. So the magnetic fields combine and produce a massive, what we call, magnetic recombination event. Now, one example of this is similar to what happens in our sun. We have the coronal mass ejections and solar flares, but this is happening at a much larger scale. So once the gamma ray radiation is spent, the material force, now we're moving rightwards in the figure, until it collides with the medium that is surrounding the star, what we call the circumburst medium. So here the material begins to decelerate and emit radiation in lower wavelengths. As the jet begins to decelerate, first we have X-rays, later on optical, then infrared, and all the way up to long wavelength radio, which happens over a period of time ranging from hours to months. The next video, please. The next slide, please. This is a simulation of a short year. Now, just before the merger, we expect the image of batteries from the and when that continues to flow, it collides with the circumference medium and begins to emit radiation in other wavelengths. So let us move on to the next slide. Okay, so what are the main motivations to study GRB? So we've looked at the picture of what GRBs are. Keeping that in mind, every time that we detect a GRB in some part of the universe, we know that a new black hole has formed there. Now, black holes, as you know, are the most mysterious objects in the universe. Neither the physics that occurs near the black hole nor the physics of their formation is fully understood. In principle, GRBs can give us the unique opportunity to study their formation. Now, long GRBs are accompanied by hypernovae, which are the most energetic supernovae that we know of. By detecting GRBs, we can also detect these supernovae up to much greater distances than those for isolated supernovae. Short GRBs lead to kilonovae, which are a unique class of novae. The intense conditions of these collisions trigger the rapid neutron capture process, which synthesizes heavy elements like gold, silver, and platinum. Now, kilonovae are known to be a major source of the production of the heaviest element in the universe. Moving to the bottom of the image, because of the wavelength range over which these GRBs produce intense radiation, from gamma rays all the way up to radio, they provide a unique opportunity for simultaneous observations across all areas of astronomy. In fact, most of the world's major telescopes observe GRBs as one of their main science goals, right? Ranging from X-ray all the way up to, from gamma rays all the way up to radio. Next slide, please. Now, space telescopes are limited to high energies at about tens of giga electron volts or billion electron volts. That's billion times the energy of visible light photons. But we know that there is much higher energetic radiation that GRBs can emit. So enter the next generation of ground-based telescopes called imaging atmospheric Cherenkov telescopes. Here are a couple of examples: HESS, the high energy stereoscopic system, and MAGIC, the major atmospheric uh, gamma ray imaging telescope. Now, what is Cherenkov? Moving to the top left of the image of the slide, when a particle travels faster than light in a medium, and that's not a violation, it cannot travel faster than the speed of light in vacuum, but it can travel faster than the speed of light in a medium. So when that happens, it emits what is known as Cherenkov radiation, which is a kind of electromagnetic shock radiation. This is similar to something traveling faster than the speed of sound in air and which produces a shock wave called a sonic boom. Okay. Now, when a high energy particle hits the upper Earth's atmosphere, because it is very energetic, it creates a shower of particles that are traveling faster than the speed of light in the medium. So each of these particles emits Cherenkov radiation. These ground-based telescopes capture these secondary showers, and from these they infer the properties of this high-energy particle, such as its energy. So as you can see, there are many reasons for studying GRBs. The next slide, please. Apart from radiation, we have now entered a new age of astronomy, what we call multi-messenger astronomy. We now see the high energy events in gravitational waves as well as neutrinos. So on the left, you have LIGO India, right, which is one of the LIGO centers around the world, and it observes gravitational waves from space. On the right, you have a schematic of the ice cube neutrino experiment. Okay, this is where they have detectors that are about 2 kilometers deep under the ice of Antarctica. Now, neutrinos are elementary particles. They don't interact with matter in any way but via the weak interaction. So, one of the reasons we study them is when you have a supernova, such as a core collapse supernova, the most energetic supernovae, it is the neutrinos that actually cause the explosion of the star. And yet we hardly see them. We know that they carry huge amounts of energy, and we can't see them. And we know that neutrinos can be accelerated to super high energy. And among all the accelerators in the universe, GRBs are expected to be the ones that can produce the most energetic particles. In 2017, as you may know, for the first time, a gravitational wave detection was coincided with the GRB. Right? This remains the only detection where the object is known. Because a short GRB, and remember, a short GRB is due to the merger of two compact objects, a short GRB and a gravitational wave detection were in the same location. This confirmed that short GRBs are indeed due to the merger, in this case of two neutron stars, and that they can emit gravitational waves of specific signature. Well, this actually led to the Nobel Prize later, and that's another motivation for studying GRBs because they are the best candidates for multi-messenger astronomy. Next slide, please. So coming to the history of GRBs, even though we needed space technology to do high energy astronomy, the motivation to do high energy astronomy had existed far earlier. Since the 1900s, physicists were aware of the existence of energetic ionizing radiation around them. Basically, ionizing radiation creates charge by stripping electrons off of atoms. So they're very energetic. Right? By this time, physicists knew that matter was made up of atoms and that atoms were made up of positively charged nuclei surrounded by negatively charged electrons. They had begun to use these devices called electroscopes. So this is a schematic of an electroscope. Essentially, the electroscope consists of a pair of very thin gold leads in an evacuated bottle. A very small force is sufficient to move them, and they are isolated from each other. So when charge, say a positive charge, is deposited on one of the leads, it pulls negative charges towards it on the opposite gold leaf while repelling positive charges. This creates a force which draws the two leads together. Okay, and just to see this a little better, please move on to the next slide. Here's a video of an electroscope in action. So when you place a charge on the brass disc, right, notice how the gold leaf rises up. Next, what he does is turns on X-ray gun, and notice how even though there is no contact of the X-ray gun with the electroscope, the gold leaf is affected, right? And he turns on the X-ray. So there was this invisible radiation which they knew had to be very energetic that was making these gold leaves move spontaneously, but they had no idea what the source was. So going on to the next slide. Around this time, okay, I seem to be missing a slide here. Okay, never mind. We can move on to the next slide. So around this time, the Austrian physicist Victor Hess began conducting manned balloon experiments to study the nature of atmospheric ionization using electroscopes. Now, in his flights, he had gone up to altitudes of several kilometers and found that, surprisingly, the intensity of ionizing radiation increased with altitude. Okay. Now, had it been an Earth-based source, you would expect exactly the opposite, right? The further you move away from the Earth, if that's where the source is, the smaller the number of detections that you should receive. But as we moved higher and higher, the number of detections increased, and this all but confirmed that the radiation was extraterrestrial in origin. Victor Hess won the Nobel Prize for the discovery of cosmic rays, and this was a term coined by Robert Millikan, another Nobel laureate. Cosmic meaning from the cosmos or from the universe. So I apologize that I'm missing that slide here. Coming to this slide, what we're looking at is a schematic of how sounding rockets work. Okay, so a major leap happened during and right after World War II. World War II was a period of rapid development of technology. This included the development of rockets by the US and the Soviet Union, as well as the development of more advanced radiation detectors like the Geiger-Müller counter. They began to use these sounding rockets for much higher altitude experiments. Now, these are called sounding rockets because the name comes from the nautical term to take a sounding, meaning to make a measurement, okay, which was usually what they did with sonar. Once the rocket is launched, the sounding rocket consumes its fuel during the rising portion of the flight, as you can see in the figure. The payload, consisting of detectors, separates from the rocket, takes readings for its time of flight, and is then landed safely via a parachute. The first scientific flight of a sounding rocket in 1949 showed unambiguously that the sun emits X-rays. This was the first instance of a source of high-energy radiation being positively identified. Later in 1962, a sounding rocket experiment identified the first extrasolar X-ray source, Scorpius X-1. Sounding rockets are still in use today by all the major space agencies as well as private companies like SpaceX, as they allow for many preliminary tests of technology without having to go to space to test them. So moving on to the next slide. Thank you. In the 1950s, the US and the Soviet Union were involved in an intense space race. With the launch of the Sputnik 1 satellite seen here in 1957, humanity had entered the space age. It was then that the high energy astronomy took big leap forward. Next slide, please. On the left, you're looking at two Vela spacecraft. Initially, space technology was in the hands of the military of the two great superpowers, the US and the Soviet Union, right? The Vela satellites were a series of military satellites that were launched by the US military with the intention of detecting any atmospheric nuclear tests carried out by the Soviet Union. The Partial Nuclear Test Ban Treaty had just come into effect in 1963. The US and the Soviet Union had agreed not to carry out nuclear tests in the atmosphere or in outer space. Nuclear explosions are very energetic, and the initial pulse from a nuclear explosion is seen in gamma rays. The Vera satellites were always launched in pairs so as to better triangulate the position of these detections. On July 2nd, 1967, two of the Vela satellites detected a flash of gamma rays. This is shown in the right-hand side picture. The Vela satellites 3 and 4 both detected this flash. Now, uncertain what had happened, but at the same time not considering the matter very important, the Los Alamos team filed the data away for further investigation. As additional Vela satellites were launched with better instruments, the Los Alamos team continued to find inexplicable gamma ray flashes in their data. It took them some time, But by analyzing the different arrival times of these flashes as detected by different satellites, the team was able to determine rough estimates for the sky positions of 16 such flashes. Okay, they definitively determined that these did not have a terrestrial or a solar system origin. After a thorough analysis, the findings were published in 1973 as an Astrophysics Journal article entitled Observations of Gamma Ray Bursts of Cosmic Origin. And it was at this point that the rest of the world became aware of GRB. And contrary to rumors and conspiracy theories that persisted for many years after the data was published, this discovery was never kept classified or top secret. Moving on to the next slide, please. Now, very little progress was made for the next 2 decades, right? Less than 100 GRBs had been determined, and there was very little idea of what they were. High energy astrophysics took a big leap forward with the launch of the Compton Gamma Ray Observatory in 1991. It was the heaviest astrophysical payload ever flown at that time, weighing 16,300 kilograms. So in the image, you have the Compton Gamma Ray Observatory on the left, and this is an actual photograph. And on the right, you can see the bottom right, you can see the four major instruments, right? Of these, I'll focus on the battery instrument, the Burst and Transient Source Explorer, because this really is the instrument that gave us most of our knowledge of GRB. It was deployed in low Earth orbit at about 450 kilometers so as to avoid the radiation from the Van Allen radiation belt. This is the belt created by the interaction of the solar wind with the Earth's magnetic field, right? The battery instrument over the next 10 years discovered about 2,700 GRBs. Now, despite the detection of so many GRBs, over the next decade, their origin remained a mystery. Now, why is that? The primary challenge to gamma ray astronomy is the very poor localization of sources, often as large as 20 square degrees of the sky. There are very large number of sources in such a large piece of the sky, and it was impossible to determine which source was actually responsible for the GRB. And if you don't know what they are, then you don't know how far they are, and you know nothing about how energetic they truly are, right? Sorry. So, moving on to the next slide. One of the biggest challenges in astronomy is knowing the distance to the source. So, here is just a simple example to explain this. If I were to take a 10-watt bulb and a 1,000-watt bulb and place them very far away, just excuse me. Yeah. So, if I were to take a 10-watt bulb and a 1,000-watt bulb and place them very far away, such that I can't see the bulbs themselves, all I can see is the light from the bulb. Now, if I were to place them at such distances that they both appeared equally bright at my end, I would not be able to tell one from the other, right? For that matter, I would not be able to distinguish between these two bulbs and any other bulb of any wattage. So coming to GRBs, just detecting them is of no use. If we don't know how far they are, we have no idea how bright they are. So coming to GRB models, a comet hitting a star somewhere in our Milky Way would be just as valid as a jet from a massive collapsing star at the end of the universe. We simply could not differentiate between these models. But during the CBRO period, the first afterglow, that is the aftermath of the gamma ray jet in lower wavelength, was detected by the Dutch-Italian Beposat mission. Now this showed the importance of follow-up observations at lower wavelengths, because now we knew that GRB is also emitted in low wavelengths. This is because in the lower wavelengths, we can study the spectrum of sources and use these to accurately determine the distance to the source. Next slide, please. So keeping this in mind, the Neil Gehrels Swift mission was launched. It was dedicated to solving the GRB mystery by enabling rapid follow-up observation. Okay, that was its main scientific goal. It consisted of a large field of view burst alert telescope to continuously scan the sky for GRBs. This instrument was coded with a shadow aperture mask. I'll come to that in a moment. It also had two other telescopes, an X-ray telescope and an ultraviolet cum optical telescope with autonomous slewing capability. That is, these telescopes could point to any position in the sky at the request of the satellite itself without human intervention from the ground. So how does this work? When a GRB is detected, the coming to the bottom left of the screen, when a GRB is detected, the coded aperture mask, right? It's basically coding of light and semi-light and dark pixels on the detector. So this coded aperture mask causes a shadow pattern on the detector. The pattern is analyzed on board by computer-based algorithms, and the satellite begins to move to better localize the positions of the GRB. Once the GRB position is better localized, the X-ray telescope and the ultraviolet optical telescope turn to this position and start scanning it. They often find the source with a localization of even up to arc seconds. This data is then sent to the ground via the TDRSS, the Telemetry Data Relay Satellite Service, a network of satellites around the world that have enabled fast communications between a mission and ground stations. Right after that, notifications are sent around the world. Other astronomy telescopes such as optical, radio, etc. then point to this location and start observing. And all this can happen even without human intervention. So thanks mainly to this mission and its enabling rapid follow-up observations, the GRB mystery was finally resolved. Long GRBs and supernovae were simultaneously observed, proving that long GRBs were indeed due to the collapse of massive stars. Many afterglows were observed, ranging from the X-rays all the way to the lowest frequency radio waves, showing first that GRBs were indeed highly focused jets, and then spectral analysis of the lines observed in the afterglow spectra allowed for very precise determination of their distances. We now routinely observe GRBs using a wide variety of space and ground-based telescopes. So next slide, please. So it's just a summary. We observe them routinely at a rate of more than one per day now. Because they're such extreme events, we are able to use them to test theories of quantum gravity as well as test the special theory of relativity from distances across the universe. We have some evidence that there may be subclasses of GRBs because we found some short GRBs that behave like long ones and vice versa. So we're trying to understand these. And there's a host of new GRB missions with new capabilities that are being launched. One of the main reasons for this is short GRBs last for less than 2 seconds, are much harder to detect, right? But now that we know that short GRBs are associated with gravitational waves, there is a huge push to improve their detection. Okay, next slide, please. So, what is India's involvement in high energy astronomy? India launched its first high energy and multi wavelength observatory in 2016 called AstroSat. Okay, this mission is closely modeled after the very successful Neil Gehrig's Swift mission. It is also capable of studying gamma rays, X-rays, UV, and optical emission from sources simultaneously. Uh, the one area in which AstroSat has a unique capability is it is able to detect something called the inverse Compton emission from GRB. This is the kind of emission that we see when high energy particles such as electrons collide with low energy photons, and this collision can raise the energies of these photons to very high energy. So what this can help us do is better understand some of the missing components of how we actually produce these gamma rays from these gamma ray bursts. Now, apart from detecting more than 100 GRBs, it has made several notable discoveries, such as detecting the first ultra-luminous pulsar in the Magellanic Cloud and observing strange repetitive X-ray emission from the black hole Swift J127. Okay, next slide, please. Okay, this is Hagar, the high altitude gamma ray telescope at Hanle. Now, this is India's mid range imaging atmospheric Cherenkov telescope. Its high altitude allows it to capture enough Cherenkov photons to still allow the use of a smaller telescope. Right? So, Hagar is smaller than the traditional telescopes like HESS and MAGIC. Its main goal is to bridge the gap between high energy space missions like Fermi and the traditional larger Cherenkov telescopes like MAGIC and HESS. A main motivation to access this regime is that the number of high-energy astronomical sources observed near the limit of space detection capabilities is about 100. Right? That limit lies at about tens of GeV, while the number of sources detected above 250 GeV is less than 10. So Hager's primary science goal is to bridge this gap and determine why sources seem to stop emitting in this regime. Next slide, please. Given the enormous power of these high energy sources, I think it is natural to ask if they are a threat to life on Earth. So what you're seeing here is the five major mass extinction events in Earth's history. The events are marked by the peaks that you see. Recently, some scientists proposed that the second most prominent mass extinction event in the Earth's history, called the Ordovician Siluvian extinction, could have been due to a GRB pointing towards the Earth from about 10,000 light years away. Okay, even at that distance, these GRBs can be life-threatening. They showed how their model correctly predicted the level of ozone depletion as well as the subsequent ice age that followed. Now, based on GRB rates, we believe, although we can't prove this, we believe that the Earth would have been hit by such GRBs that could cause extinction level events at least twice in Earth's history. So we have to, this is another motivation for us to observe these GRBs, right? We need to get a better measure of how often and from how far we can see them. Then we will have a better estimate of what threat they actually pose to life. So, next slide. Thank you. And I'll take the questions now.
Thanks, Ashwin, for great session. Anybody has any particular question, do let us know. Yes, Bharat sir.
Yeah, I have a question for Dr. Ashwin. My
Yes,
question
sir.
is very simple. We used to observe on the photographic, not photographic plates, emulsion plates. And later we were able to even pick up these gamma rays on bubble chamber also. So
Hmm.
my question to you is, the methods which were used in India at TIFR were the following. One was taking the plates all the way up, emulsion plates all the way up into atmosphere, above atmosphere, by using balloon. And these plates were exposed to the radiations which were coming down from the upper atmosphere, or rather from the cosmos. So these were actually, we could actually see the particles making a twin pronged in the emulsion plates, and thereby we were able to identify gamma rays in the earlier times. This method was used even by Homi Baba, our nuclear scientist, along with a group of people like Professor Vishwas and others. Vishwas was the primary person who deviated from emulsion to plastic plates. But the earliest observations which were done were primarily done using emulsion plates to look for high energy particles coming from the cosmos and collecting on the emulsion plates. And this one had to do is, we used to use emulsion plates and use a microscope and see through the microscope. So it used to be a stack of emulsion plates, and from that one could actually calculate what would be the velocity and what would be the mass for all these particles which are coming down. There were very eminent people like Professor Rajaramana Udgaonkar. All these people were associated with particle physics, and the usage was only nuclear emulsion plates. And Professor Vishwas later expanded to Lexan plastic plates. So even the plastic plates were analyzed for looking at these particles. So why I had to bring back some background history is primarily to tell you that the research of high energy physics began during the time of Homi Baba, much before independence also, and the work was going on until 74 when election plates came. The another option which came up was during Professor Bishwas. They used a space shuttle called, and the mission was known as Anuradha. And in Anuradha, these Lexan plates were used to identify high energy particles, including gamma rays. So this is few inputs I thought I should share with you because many of our friends who are here would like to know whether this kind of work was happening in the past. And the answer is yes,
Yes, sir.
it was happening, and it was actually one of the missions of the balloons, sending the balloon up was even Dr. C.V. Raman was primarily at Bangalore, and there they did this experiment, and later on a host of our cosmic ray physicists could identify gamma ray particles in these emulsion plates. Even other particles they were able to identify. So this is just to give you some input that people were actually understanding the particles. So this is all what I had to share with you, Ashwin. And your talk was very good. And I always ask our participants also to talk about this because one must know a good background history of how earlier works were done and how the present work is coming up. You nicely put up the topic of gravitational waves using LIGO. Now, all this is an outcome of the earlier works which have been done by our own scientists, and it was really remarkable. So, thank you, Ashwin, for bringing these new aspects. And also, I would like to share with all of you that we have a group in IIT Bombay. Varun Bhalerao is the person whom I have known him for many years. Looking at gamma rays. So this is what I had to share with you. Thank you.
Thank you, Bharat sir.
Thanks, sir, for that enriching
Yeah.
background.
If there are any more questions, please.
Yeah, we
Amula
have
had
There
some
are a couple
queries
of
for you, questions
questions in
for you.
the
Amula,
uh,
sir, there
uh,
are two questions which
or
has come
anyone
from
can ask a
yeah.
question here because the
Mangesh sir, you
speaker
have
is
a
here with
question which
us.
is
So you are welcome to ask any number of questions. Am I right, Ashwin?
yeah,
yes,
yeah,
sir.
Bharat sir, we have
Any
couple of
questions, any number of
questions.
questions are
We
fine.
have couple of questions come from
Mangesh
our.
ji, do you have any questions?
Yeah, Bharat sir, I'm just asking
Yeah,
couple of questions which are there in the chat.
thank you.
How do
Ravi,
scientists know and
Okay.
when and where?
Yeah, go ahead.
are you
May I?
conducting any further research, Ashwin, from your
Not
place, from
not at the moment.
Mangaluru?
Not at the moment, sir. I've taken a bit of a sidestep from gamma rays to
Excuse
radio
me,
astronomy.
Ashwin. Are
Yeah.
you conducting any further work on this?
Not at the moment, sir. No research on gamma rays at the moment. Have some plans, but not at the moment.
Uh, okay.
Yeah, so let me just take up these questions. Amoli
Yeah,
ma'am has asked a question about the amount of matter from black holes. So basically, what we believe is just because before the final merger into a black hole, right? We have a short-lived supermagnetar. A magnetar is a very highly magnetized neutron star. This is the point at which we believe the matter is ejected, right? So just before the final collapse into the black hole. And one of the reasons we believe this is jets are very effective at shedding the excess angular momentum that has to be shed before the whole thing can collapse in. Okay, so we believe that GRB occurs just before the black hole is formed.
Right.
Does that answer your question, Amoli ma'am?
So yes, a bit. And one more thing, sir. The next question is regarding the GRB. Do they actually produce the gravitational disturbance?
Yes, they do. They do.
And are they detected by the LIGO which you mentioned?
Yeah, in fact, in 2017, we had the only known detection up to that point, right? So basically, what
Okay.
happens is gravitational waves are detected. Now, with
Okay.
gravitational waves, it's very difficult to know where they come from. But then you can think about using timing, right? When you see a major detection and at the same time they observed a short GRB, right? Within a split second of each other,
Yeah.
right? So you can say that that is not a coincidence. There's a lot of analysis that they do about these things and give you the probability that this detection is not a false detection and all these things. So they quite
Okay.
confidently identified a short GRB with a gravitational wave, and moreover, the detection is what comes from. Basically, there are different kinds of how should I put it, signatures, right? And this particular signature of the gravitational waves was that from a merger, only an
Okay.
object, because there's a distinctive signature for inspiraling binaries,
Okay.
right? So
So, but
everything from the space.
as you said that GRBs travel very slow when they are not in a medium, and they travel faster in a medium. So, how do they actually produce the gravitational disturbance when they are in the space area?
Okay, actually, you don't need a medium, right? Just as we
Yeah,
know that light travels through space,
yeah,
right? And the one missing component in what is called the standard model was basically each of the other three fundamental forces, right? They have these force carrier particles that mediate any interaction. So, see, in modern theories, when you say that the proton and electron interact, what they believe is there is an exchange of virtual photons between them. Otherwise, how do they know they exist, right, in empty space, right?
okay,
That's kind
okay,
of a philosophical problem called action at a distance. So when it came to gravity, we had no clue, right? And there was one previous indirect detection called the Hertz-Taylor binary in 1976, where a lot of energy was found missing, and they found the model showed that all the missing energy corresponds to what is predicted for gravitational wave emissions. So that's why the search
okay,
started for actual gravitational waves. There was an indirect detection, they wanted to detect it directly. And that is what LIGO and advanced LIGO are now achieving. So we
yeah,
now know that there are these things called gravitons, just like photons, right?
yeah,
And they can
yeah,
mediate between gravitational disturbances, just like photons do between charges. So
okay.
it was really
And
a
sir, if
fundamental discovery.
yeah, sir, if I may ask you one more thing, how does the GRB affect the life on Earth?
If it happens, see, it all depends on how far away it is.
Yeah,
And
but still, how like if we are in the range of any kind of GRB, how will it really affect us? Because as you said, it moves really fast.
okay,
So
so
I really
here are the estimates. Okay,
okay.
at a distance of about 1,000 light years, a GRB can potentially wipe out Earth's atmosphere
Oh,
at a distance of
okay,
1,000 light years. Now, fortunately, the probability of such a GRB occurring within this distance is very, very, very low as far as we know, right? We need to still do further
okay,
studies to improve the understanding of rays. Um, from about 10,000 light years away, there is still a potential danger. So what happens is
okay,
these high energy radiation, they can basically produce nitrous oxide in our atmosphere and other oxides of nitrogen. These immediately
okay.
begin reacting with ozone,
Yeah,
okay, and they can deplete the ozone layer. So once the ozone
yeah.
layer is depleted, you can imagine what happens next.
Yes,
Over a
sir.
period of
Yes,
months,
sir.
we have a, I would call it a slow death of life on Earth, at least on land.
Yes, sir. Yes, sir.
So it depends on
Thank
a
you,
lot
sir.
of
And it
factors.
was really lovely to hear from you. So it's a
Thank you,
wonderful
Molly, ma'am.
topic.
Likewise, a pleasure to talk to you as always.
Thank you, sir. Thank you, sir.
Thank you. There were some other
Ashwin,
questions.
We have two questions in the chat box which has been
Okay,
shared
go ahead, sir.
to us. So first is, how do scientists know when and where a gamma ray burst happens? Basically, you talk about the gravitational waves and all. So you can add on to that.
Okay, so the most
Is it a
early.
recorded session?
Yeah, yeah,
Uh,
Arka, go, which is recorded. Ashwin, go ahead you with your answer.
okay,
Well, the
so
recording will be available now because whoever have been missed the meeting materials, where should it be available? Is it YouTube platform, social media platform?
Thank you, Arka. Over to you, Ashwin.
yeah, so
My question is where the meeting recording materials will be available.
this will be made available.
We will share you
Mangesh
the
sir
link.
will.
Arka will share you the link.
My question is where it will be available. What the platform name?
It will be available on
Is
Google
it
Drive.
YouTube? Is it social media platform like Facebook, Twitter, any kind of platforms? What's the name of that platform? That's my specific question.
Arka, the link will be shared you on the Google
The
Drive
link
of
will be
our
shared. I am not interested in that. I am asking what's the name of that platform. Whenever the link will be shared, I may not be there. That's not my question right now.
be shared on WhatsApp.
It will be shared on WhatsApp, not in any kind of social media or YouTube platform, right?
No, no.
Okay.
Okay, Ashwin. I think sorry for the interruption. You can
No
continue.
worries. So okay,
No, it's not interruption. It's a question.
right.
I
So
think Arka, we have answered your question. We
Yeah, but lately, unfortunately, by the way.
thank you. Yeah, Ashwin, go ahead.
okay, so basically the brightest component of gamma ray burst is in gamma rays, right? So it's the gamma ray detector that first sees a flash. Now, this is the issue that I kind of discussed in my talk. It's impossible, even to this day, we are not able to collimate gamma rays. So I'll show you that literally, because this is what a top gamma ray scientist showed me, right? If you see a gamma ray, you can tell with all your most advanced technology in gamma rays that it's somewhere over there in the sky. He raised his arms wide, right? Practically showed me 1/10 of the sky. So one can imagine how many sources are in such a big piece of the sky. Now, the only way that we can actually localize them is if we have these rapid follow-up observations, right? And these things need to be done within minutes from gamma rays to X-rays. And that is why the Swift mission was launched with exactly that goal. So a gamma ray burst happens, immediately this XRT points towards it, right? There's a special algorithm that localizes it. XRT points towards it and starts scanning. So once it scans, it's able to find it in some location, right? It immediately sends an alert to the ground station. So that localization, there is what a person called a burst advocate who sits there, looks at that, fine tunes it, and then sends an alert to the entire network. So people are waiting on their smartphone. The moment they receive that alert, right, they basically ask their robotic telescopes to point to that location. And that is when we get a whole rich range of information. And then we know what the GRB is, how far away it is, how bright it was, etc. I hope that answers your question.
Yeah, yeah, absolutely. That's fine. There is one more question from one of our students. How do astronomers measure the distance to a gamma ray burst? I mean, how do they? How far?
Okay, that is a very good question, right? Because that was also one of the greatest challenges of high energy astronomy. First of all, we don't do it in gamma rays because we can't, not yet. But when if you're familiar with what a spectrum is, right? You look at a star. When you look at a star like the sun, you see all these emission and absorption lines, correct? So these lines are specific to the element that emits them, and they also belong to what we call transitions of electrons from one level to another level to another level. So carbon might have a few lines, iron might have a few lines, right? These lines are visible from X-ray and downwards. Now, this is something I did not touch upon, a bit complicated. For when you look at very, very distant sources, we have to worry about what we call cosmological expansion. Right? From the Big Bang, the universe has been expanding. And a very big surprise is that expansion is still accelerating. Now, what this does, right, it creates something called cosmological time dilation, which means all the photons, in fact, you can say the whole of physics is stretched, right? So if a photon started from a GRB at a certain energy, by the time it reaches us, it has reduced in energy or frequency. Okay, so if imagine that an element, like let's say iron, emits a photon with a certain signature line, right, at about 5 point something keV. By the time it reaches us, it is shifted to a different energy due to this cosmological effect, expansion. And mind you, this is different from a Doppler shift. Doppler shift is due to the motion of the source. This is due to the expansion of the universe. So when we see the shift and we see multiple lines that have shifted to the same degree, we can then use a cosmological model to see how far the GRB is. Okay, this is a bit of a complicated question, but shifts in lines in the spectra, and when we see the same shifts across different lines, we can use that to say this is how much the universe has expanded since light from here came to us, and then we get the distance to the GRB. Is that Does that answer your
Yeah,
question?
yeah. Thanks, Ashwin, for that. I think we have one more participant. Abhinav, you have a question?
Yes, sir. Good evening, Ashwin, sir.
Good evening, Abhinav. Nice to hear from you again.
Yes, last time we met at IID quiz.
Indeed, and you were one of the finalists, which I should point
Yes,
out here at the national level quiz.
yes. Sir, my question is that you mentioned that neutrinos rarely attract with matter.
Yeah,
So how we detect them? Like ice
rare,
cube.
very good question. Not rarely is correct, but they do interact, right? Even if they have a one in a trillion chance of interacting, if you wait for a trillion interactions, you may get one, right?
So then how they are detected at ice cube observatory?
Okay, so this is what happens. You have this very thick layer of ice. Any charged particles, cosmic rays, other kinds of matter would collide with one or the other ice particle, right?
Yeah,
And be stopped right there. It will be attenuated, right? So most of these other particles will be filtered at the top level. Only neutrinos will pass all the way up to the bottom. So this
yes,
is kind of like a sand filter, when you use sand as a coarse filter. It basically gets rid of all the particulate matter, but it allows the fine water molecules through,
yeah,
right?
yes,
So if you wait long enough, all the other particles are attenuated, and what's left behind should be neutrinos, and that's how they're detected.
yes. Thank you, sir.
You're welcome.
Yeah.
Thanks, Abhinav. Thanks, Ashwin. We have one question from one of our participants, Ravi. Uh, he's saying, are gamma rays created when a true sun diving comet plunks into our sun?
Uh, Gamma rays somewhat unlikely, but I mean depends on the size of the comet, right? Depends on the size of the comet. Depends on the speed of the comet, but it's unlikely that a solar system comet would actually produce gamma rays from the sun.
Okay. Anybody else has any question? Gopalan? Yes, Gopal.
Hello, it was a very nice presentation. I enjoyed it. I had a
Thank you.
question out of curiosity.
Yeah,
Um, One is that I thought the Kolar goldfield was being used to measure neutrino.
it was.
Um,
It was.
so, is that experiment not successful, or has it been abandoned? Or
Uh,
um,
I do not know, to be honest. This was an
okay,
experiment carried out a long time ago, right?
yes,
Right,
yes,
and some of my peers had actually told me about it. They were involved in this experiment. People from
right,
KIFR.
right,
Uh, so I don't know. I do not know if they actually detected neutrinos. I think that would have been big
okay,
news.
okay.
But
Uh,
I'll have to get back to you on that. I don't know.
Okay, that's fine. I just follow up on that. Is there an advantage to using the polar ice as a shield compared to the rocks of the? Is there any interaction difference for stopping or filtering out the cosmic rays so that it's easier to detect the neutrinos? Is there anything like that in terms of particle interaction, or it was more of convenience to put it out in the Arctic or Antarctic below the ice sheet?
That is, well, this is actually not my field, but
Okay. Okay.
I think that may be because before the ice cube experiment, there were two experiments, Kamiokande and Super Kamiokande, that
Right.
used ultra pure water.
Yes.
So first it's water, now it's ice. So
Yes.
I wonder if that has something to do with it. So
I
we'll
see.
have to look into it.
Okay. Okay. Thank you. Thank you. It was a very nice presentation. Thank you.
Thank you. Thank you.
Thanks, Srinivasan sir. Thank you. Anybody has any question?
Sir, Amoli here. So
Okay.
I just wanted to ask you if you could explain in some other session regarding the GRBs taking the same topic, but in a bit simpler manner because people like me who are not from physics background but are interested to learn topics like these. So it would be really nice for us.
Yeah,
Uh,
basically, Ashwin is starting to Amoli's topic. Since this topic needs a lot of understanding of physics and and study and all. So basically, there are some questions from one of our participants also that how does a normal like day to day way the amateur astronomers can know more about the GRBs and what they can contribute
okay.
to studying of them.
I will say that's a very good question. In fact, in the interest of time, I left this out, right? Not just the interest of time, because unfortunately, my answer will come as a bit of a disappointment. At this moment, there is very little that amateur astronomers can do when it comes to GRB, right? The reason being that in order to detect these, so we can't detect gamma rays directly. We don't have the means. Um, what we do is, if at all anything, we would use, say, our optical telescopes and think of looking at the afterglows, correct? But even the world's biggest telescopes, like Subaru and the ones on Mauna Kea, right, Gemini, etc., sometimes look at these GRBs and detect nothing. So, what chance do we have with our 6-inch and 10-inch? So, practically none, right? But having said that, it is not impossible. There is a record set by someone who's actually a scientist who used, I think, a 10-inch telescope with a CCD camera and managed to barely detect a GRB. So it's not impossible. The way to go about this is to, and this is something that I have in mind, right? The way to go about this is to sign up with something called the GCN, the Global Coordinates Network. So I mentioned that when GRBs are detected and rapid follow-ups are enabled by sending alerts, right, to people who are signed up for it. So even we can sign up for this. And there was one burst. I can tell you very clearly. There was one burst. It's designated 08219b or C, I think. It was called the naked eye burst, where from billions of light years away, it had such a bright optical afterglow that it was almost visible to the naked eye, right? So I can say that it's difficult but not impossible with our amateur telescope. Apart from that, speak to Shovan Acharya sir, we have a citizen science project called the Burst Chasers project that is on
Yeah, yeah,
the Zooniverse platform. And I think
yeah.
down the road we expect many more GRB citizen science projects. So you can definitely get involved in one of those, right? Amoli madam here is one of the experts on citizen science projects, and many others in our network are there to help you if you want any help with that.
Sir, could you suggest any of the books with respect to particle physics, some basics of particle physics? If you could just message us or something like that, so that we can just go through and learn some basics of physics.
I will basics. Okay, so unfortunately, with GRBs, we are not dealing with just particle physics. We are dealing with every
Yeah,
part of physics, right? I mean, we are dealing with gravity that we don't even understand. We are dealing with energy productions we don't understand. So most GRB physicists, they pretend to understand these things. They just hope that nobody asks them a question that they can't answer, right? So uh, look at it. I'll have to look into this because at the basic level also you're covering many aspects of physics, right? Many aspects
Right.
of physics, not just particle physics. You need to understand spectra. You need to understand the effect of light on matter, right? You need to understand what these transitions are, electronic transitions, which we have covered in PUC a little bit. Um, and then you need, I wouldn't say understand cosmological expansion and its effects, but you at least need to know the main result, right? Because I'm not a cosmologist. All I've ever done is use one or two equations and plugged and chugged in that. Because it was the cosmologists who did the work, I just borrowed their equations.
Okay.
Yes,
Okay.
so I'll
Uh,
since we're in touch, I'll definitely look into that.
Definitely. Thank you, sir. And Mangesh, sir, thanks for such a beautiful and learning experience which you just gave us. It was really wonderful and would like to have such topics more to be involved in the webinars. Thank you, Ashwin, sir. Thank you, Mangesh, sir.
Thank you, Amoli ma'am.
Thank you,
Thank you very
Ashwin.
much.
Thank you on behalf of all participants. We sincerely thank you for your time, effort, and enthusiasm in delivering today's session on gamma ray burst and high energy universe. I think your ability to explain such a complex, though it is a very, very complex and difficult cosmic phenomena in clear and engaging way. Definitely, the students have sparked the curiosity and inspired us to look the universe in a new wonder. We truly appreciate your passion for science and your willingness to share your knowledge with us. Once again, we look forward for more such enlightening sessions in near future. Thank you on behalf of Amateur Astronomers Association, Bombay.
Thank you very much, Mangesh sir. It
Thank
was
you.
my pleasure to come here and thank you for inviting me to do this.
Thank you. Thank you, everyone. Thank you, Srinasan sir. Thank you, Amoli. Thank you, Ravi. Thank you, Abhinav. Thank you,
Thank you, sir. Thank you, sir.
Manta. Thank you very much.
Thank you, everyone. Bye bye.